The biggest risk in your outsourced civil engineering project isn't your contractor, it's your own quality process. At AXA Engineers, where we manage over 1,000 projects annually with a team of more than 80 engineers, we see firsthand how a single miscalculation, replicated across distributed teams with varying standards, can escalate into a significant failure before it even reaches your desk. This is not a theoretical issue. It results in significant financial and reputational consequences that can derail even the most promising initiatives. A shift-left approach to quality assurance integrating it from day one is not just a best practice. It is the only effective defense against the inherent risks of modern, globalized project delivery. But what does this look like when multiple vendors and standards are involved? Consider the scenario in which two highly competent engineering vendors, each given an identical project brief, deliver work products that are fundamentally incompatible. This is a frequent and costly outcome when a unified quality assurance framework is missing from the outset. It is one of the primary failure points in outsourced engineering, and understanding the underlying mechanics is essential to preventing it. We have built our delivery model on neutralizing this risk. Technical skill alone, without process standardization, is unreliable, especially when managing the complexities introduced by multiple independent teams on a single, intricate project. Take, for example, a large-scale land development project covering several hundred acres. Multiple specialized firms are brought in. One handles site grading and earthwork, another designs the utility networks, and a third manages structural elements such as retaining walls. Each firm contributes deep expertise, but this distributed approach introduces a critical variable: each organization operates according to its own internal standards. Without a central control mechanism, this decentralization systematically lays the groundwork for project chaos. The impact of these disparities becomes clear in the technical details. The grading contractor may work using the US National CAD standard for its layering system, while the utility designer relies on a proprietary in-house standard. When these deliverables are combined, the result is a digital Frankenstein's monster: files that are internally correct but collectively unusable. Integrating these datasets requires extensive and expensive rework, causing delays and inflating budgets before any physical work even begins. This situation is similar to assembling a high-performance engine using pistons manufactured to millimeter specifications and cylinders bored in inches. The assembly process, and by extension the entire project, comes to a standstill not due to a lack of skill or effort, but because of a fundamental failure in standardization. This is the point where many outsourced projects stall, bogged down by incompatibilities that could have been avoided with proper planning. A robust QA framework addresses this by establishing a single source of truth from the very beginning. Such a framework does not stop at a general scope of work. It defines and enforces granular requirements for file naming conventions, software versioning, material specifications, and testing protocols. By mandating a unified set of standards, the QA process ensures every deliverable, regardless of origin, integrates seamlessly into the master project model. This alignment transforms a collection of independent vendors into a cohesive project team, minimizing the risk of integration failure at critical milestones and preventing the chain reaction of delays, cost overruns, and disputes that arise from incompatible data. Yet, even with rigorous standardization, errors, human or computational, are inevitable. The next challenge is tracing a single calculation error back to its source within a complex web of hundreds of revisions submitted by teams across different time zones. Without a structured system, projects face a black box of accountability. A critical error in a drainage calculation or a load-bearing assumption can lack clear ownership, stalling progress until the source is found and corrected. Strategic QA resolves this with a transparent, immutable documentation trail. This system functions as the project's flight data recorder, logging every revision, comment, and approval with timestamps and author attribution. The result is a comprehensive, verifiable history of the project's evolution. When an error surfaces, project managers can quickly trace it to its origin, pinpointing the specific revision, author, and submission time for targeted correction. That transparency shrinks error investigation from days to hours, allowing the team to maintain momentum and focus on project delivery. With standardization and accountability in place, The focus shifts to proactive mitigation, identifying and eliminating errors before they ever reach the field. The most dangerous error in a civil engineering project is not a visible crack in a foundation. It's a flawed assumption buried deep within a spreadsheet, a value that appears fully compliant on paper but is physically unviable when translated to the material world. These latent errors, often related to geotechnical properties or material performance under specific environmental stressors, represent the greatest threat to a project's integrity and public safety. Identifying them after construction is not an option. The only strategic defense is to prevent them from ever becoming part of the final design documents. This requires a fundamental shift in how quality is perceived and implemented, moving it from a final inspection gate to an integral part of the initial design process. This proactive approach is encapsulated in the shift-left principle. The concept is best understood through a clear analogy. Correcting a typographical error in a recipe manuscript costs nothing but a moment of an editor's time. Discovering that same error, a misplaced decimal, in a measurement, for instance after the cake has been baked and subsequently ruined, means the entire investment of time and materials is lost. You must start over from scratch. The exact same logic applies to infrastructure, but with exponentially higher stakes. The cost to correct a flawed design assumption at the conceptual stage is minimal. The cost to rectify it after concrete has been poured is astronomical. This is why firms like AXA Engineers structure their service offerings around this principle, positioning QA not as a cleanup crew, but as a foundational element of project strategy from day one. Viewing quality control as a final safety net is an admission of process failure. Proactive quality assurance, in contrast, is an offensive strategy designed to find and eliminate these recipe typos at the earliest conceivable moment, long before they can contaminate the project's later stages. This method directly connects to mitigating public safety risks by moving beyond simple regulatory compliance. A design may check all the required boxes of a building code, yet still contain a fatal weakness. Proactive QA protocols address this by actively stress testing designs through a series of rigorous examinations. These include structured peer reviews by engineers not assigned to the project, advanced simulations to model performance under extreme conditions, and detailed constructability analyses to ensure the design is physically achievable on-site with available materials and techniques. This is the mechanism that translates abstract regulatory standards into resilient, safe, and durable public infrastructure. Consider a major bridge project where a subtle miscalculation of harmonic resonance was overlooked in the initial design. While compliant with static load requirements, a proactive QA process involving dynamic simulation would have identified the vulnerability, preventing a potential wind-induced structural failure and averting catastrophic consequences. This proactive defense naturally evolves from simply avoiding failure to actively building an elite institutional reputation. The long-term value of consistent, predictable quality cannot be overstated in an industry where project life cycles are measured in decades. We can visualize this through two contrasting scenarios. One engineering firm prioritizes speed and cost savings by minimizing its investment in front-end QA. Its projects are frequently plagued by requests for information, change orders, and client disputes over rework, leading to a market reputation for unreliability. Another firm, such as AXA Engineers, invests heavily in a robust, transparent QA system that is recognized by industry authorities like Autodesk. This investment fosters long-term, collaborative partnerships built on a foundation of validated trust, where clients are confident in the accuracy and reliability of every deliverable. Client satisfaction and a superior reputation are not accidental byproducts. They are the manufactured outputs of a strategic QA system. This system is engineered to ensure every drawing, calculation, and specification reinforces the client's trust, transforming transactional projects into enduring professional partnerships. A firm's demonstrable commitment to quality ultimately becomes its most powerful and sustainable market differentiator. In conclusion, the hallmark of a leading civil engineering firm is not simply the projects it delivers, but the failures it anticipates and prevents through a disciplined quality process. Quality assurance should operate as the strategic backbone of every project, not as a separate department or a late-stage review. At AXA Engineers, this philosophy underpins our reputation shifting left, enforcing standardization and fostering accountability at every stage. If you found this discussion valuable, please like, subscribe, and share your own QA challenges or experiences in the comments. Evaluate your next outsourcing partner not just on price, but on QA, all starting with a standardized shift left framework.